Okay, good afternoon, ladies and gentlemen. Today we'll do 10 series, and this series are from my 100 series video. So I have the file right here as usual. You guys can go download that in the description. And I'm not going to work out everything today because all the solutions were done in the 100 series video. It took me like 6 hours, so I'll just direct you guys to see that. So for example, the first question that we'll do today is question number 9 from the 100 series video. And again, go download this file, try the questions first before you watch it. It will be perfect. And for the people who are on the live stream, thank you so much for coming. So let's just go ahead and get started. Yep. We will just focus on which series convergence test that we need because this is meant to be for your calculus 2 final review. So the first one, we have the series as n goes from 1 to infinity of -1 to the n over square root of n plus 1. So for the people who are on the live stream, please throw in some ideas. What series test that we have to use for this? And by the way, I'm wearing my series convergence test shirt, so if you guys need help, you guys can take a look at my shirt. We have about 10 series convergence tests that we need. Alternating, good. So this right here, we will check the alternating series. Yeah. And what do we have to check though? Let's write down some key steps, but we are not going to work out everything. So what's the key step? And how do we know this right here is the alternating series test? Thank you so much. Yeah, it took me a while to design this shirt, so I love it too. Thank you. Because of the -1 to the nth power. So this right here, it alternates. Alternating in the sense that positive, negative, positive, negative, or negative, positive, negative, positive. In this case, the first term is actually negative, but the next term is positive by alternates. All right, so we do the alternating series, and this right here, just make sure that you kind of put this aside maybe. This is n goes from 1 to infinity, -1 to the n, and then we multiply by 1 over square root of n plus 1. So this right here, the non-negative part is the Bn. And there are two things that we have to check. The first thing that we check is, do we have the limit as n goes to infinity of Bn equal to 0? So that's the first check. And the second check is, do we have Bn plus 1 less than or equal to Bn? Again, that's the second check. In other words, does Bn go to 0 as n goes to infinity? Secondly, we will have to make sure that Bn is decreasing. And for this right here, you can do algebra. And for this one right here, in my opinion, it's one of the ones that's easier because there's a clear indication because of the -1 to the nth power. Hey, you just have to use the alternating series test. All right? So that's the first one. And let's go ahead and get to the next one. You can download the file in the description. So try the questions as well. Now, the second one is question number 13 from the 100 series video. If you want to see the whole workout solutions, just go check that out. And by the way, can you guys believe that I made that video like 5 years ago? Yeah, the 100 series video was 5 years ago. 2019. 2019. Yo, that's a long time. That's a very, very long time ago. Anyway, number 13, we have the series n goes from 1 to infinity, 1 over square root of n, e to the square root of n's power. And I purposely picked these questions because these are meant to be for calculus 2. For my 100 series video, there are some questions a little bit above calculus 2 level. Hello everybody. All right, so what do we do right here? The Ronald, correct. Yes, for this one, we can try the integral test. But can we do the comparison though? Well, just think about it. If you compare the series with just 1 over square root of n, you actually went up with a non-conclusive result or a wrong result. So no comparison. And if you try with this 1 over e to the square root of n, that one is not so easy to decide if it's convergent or not. By the way, if we don't have the square root of n, in fact, you cannot use the ratio test. The ratio test will give you L equals 1. So that's inconclusive. But for this right here, and yes, this is a live stream. So we did the integral last time. Today is series. And sometime next week, right, in the coming week, I will find time to do the limit and also derivative. But getting back to this, we will be using the integral test. Oh. All right, here's the main thing though. If you want to use the integral test, you have to make sure that we can integrate. So in our case here, just think about our function. Let me just say, I'll put it down here. Our f of x, just replace all the n's with x's. So we have 1 over square root of x, e to the square root of x. We can fix this a little bit. This right here is 1 over square root of x. Bring this up, e to the negative square root of x. And then imagine you have to integrate this. But before we can integrate this, we have to also make sure that our function f, there are 3 conditions. What are the 3 conditions that we need in order for us to use the integral test, besides the fact that we can actually integrate this? Decreasing, positive, and one more, continuous, correct. And for my class, I usually just ask the students, graph this on the calculator and then provide a graph. And for this one in particular, x cannot be 0, and you will see the graph will look something like this. So our function f, just mention that is positive because it's above the x-axis, and we also have continuous, right? There's no gaps anymore and all that, and then decreasing. And you have to mention that is continuous after 1 because we just care about from 1 to infinity. So let's say this right here is 1, so I'll just say 4, x is greater than or equal to 1. So you can go ahead and check the integral. Check the integral, right? You go from 1 to infinity of our function, which is that 1 over square root of x, e to the negative square root of x. And if this right here converges, then we can go back to this right here and say this right here also converges. If this right here diverges, then this right here also diverges. But make sure that if you do end up with a value right here, you cannot say this converges to the same value because they don't, right? So go ahead and work out the integral and check that out. If you want to see the solution, make sure you just check out the 100 series video. Do u sub, correct. For this one right here, just do u sub. Let me just indicate that u equal to negative square root of x. Or square root of x, doesn't matter, however you want to do it. Now you can do positive or negative square root, doesn't matter that much. Right? I will leave this to you guys. All right, moving on to number 3. Who has Cal 2 final coming? If you do have a final coming, right, Calculus 2 final coming, just dropping me in the chat so that way I know who you are. In the meantime, I'll write down the next question. This is question number 15 from my 100 series video. I just thought about this idea recently that I can go back to my 100 everything video and then just pick up 10 of them and then we can do a live stream for review purpose. Sounds great. Oh yes, AP Cal test is tomorrow, right? Yeah, best of luck on your AP calculus test. Alright, so I see a lot of you guys have your calculus 2 final. For my class is June 3rd, so another 3 weeks or so. Alright, anyway, for this one right here, what test do we need to use? Yes, the ratio test. And can you tell me what's the indication that tells you we have to use the ratio test? Because of the factorial. Excellent choice. Whenever you have a factorial or n in the exponent, ratio test is a great idea, especially for factorial. Right? And if you guys need to review, here, check out my shirt. So those are the details. Have all the series convergence tests on my shirt. But anyway though, here we do the ratio test. And for the ratio test, remember, we will have to check the limit. And this right here is our an. We check the limit as n goes to infinity, and we do the ratio of an plus 1, which is the next term, divided by the current term, which is an, and then we apply the absolute value. Because sometimes this right here might be negative, so the absolute value will take care of that. And let me just write down the conditions. Suppose we do all the work and then we end up with some number L. I will tell you this right here, the series of an converges if L is greater than, just kidding. The series an converges if L is what? I forgot, unless I go back to my shirt. So what's the L right here? What's the condition for our original series to converge? L less than 1. Yes, thank you. L less than 1. How about the next one? The series diverges if L is what? For this one, L greater than 1. By the way, for the first case, if L is 0, that's okay. For the second case, if L is infinity, that's also okay. When you do the limit comparison test, once you get the L, if you end up with 0 and infinity, you have to be careful. You actually cannot draw conclusion. But for the ratio test, 0 here, infinity here, you can still draw conclusion. However, what if L is equal to 1? Yeah, this right here, just a sad face. If L is equal to 1. But on the test, if you end up with L is equal to 1, do not just draw the sad face. You actually have to just use another test to work it out. If you draw a sad face, you can never get a partial credit or anything. Yeah, so don't do that. Alright, so I will leave that to you guys. Today, the main thing is to talk about the strategies. And then just make sure that you stay tuned, because this week I will try to find some time to do the derivative and also the limits review with you guys. Okay, next one, number 18, right? Number 18 from the 100 series video. So here we have the series, n goes from 1 to infinity, and we have sine of 2n over n plus 3 to the n. Okay, so for this one, what do we do? Yes, this is not really alternating though. If you plug in 1, we will get sine of 2. If you plug in 2, you get sine of 4. I'm just talking about the numerator. And then if you're plugging, the next one is 6, and so on, so on, so on, right? Be careful. Sine of 2, when 2 is in radian, is this positive or negative? Help me out. Sine of 2 is positive or negative? Sine of 2 is more than... No, it's not more than pi, so it's less than 180 degrees, so this is positive. Thank you. So this is positive. How about sine of 4? This right here is negative, yes. How about sine of 6? Be careful with this now. Sine of 6, this is less than 2 pi. This right here is negative as well. So as you can see, the first term is positive, the next term is negative, and the next term is still negative. So this is not alternating in the usual sense. When you say alternating series, we want positive, negative, positive, negative. Or negative, positive, negative, positive. You cannot have positive, negative, negative. No, not like that. Not like that. Not like that. So unfortunately, no alternating series test. So what do we do for this one? Can we use the limit comparison test, and how would you do so? Remember, if you want to use the integral test, one of the criteria is, can you integrate the function? Like, okay, can we integrate sine of 2x over x plus 3 to the x? Not even talking about if this is decreasing, continuous, positive, or whatnot, but perhaps the most important criteria to use the integral test is, can we integrate such an expression, right? We can actually use direct comparison test, yes. But before that, let me tell you, here's a clear indication, right? When we have sine of whatever, earlier we went over that these terms will be positive, negative, negative, and we don't like that. So let's get rid of the negative. How? We are going to check, right? Check for absolute convergence. In another word, we are going to consider the series as n goes from 1 to infinity, and let's just apply the absolute value for this right here. This is how we check for absolute convergence. And in fact, before you can use the limit comparison test or the direct comparison test, we have to make sure that all the terms are non-negatives. So that's another reason to do so too. More importantly, this right here, in fact, whenever you see sine or like sine n, take the absolute value, because I can tell you that, here's a little note. If we have absolute value of sine of something, sine of theta, what's a bound for this? What's the maximum value for sine theta? One. So we have an inequality right away, isn't it? We have the absolute value, so we can just write it down like less than or equal to 1. So right away, we can see that this right here, the absolute value of a quotient is a quotient of the absolute value. So we can say this right here is going to be less than or equal to the series as n goes from 1 to infinity. We can replace the top with 1 because sine of anything, the absolute value for that is less than or equal to 1. So the top is less than or equal to 1. The bottom, n plus 3 to the n is always positive because n goes from 1 to infinity. So just write it down. So we have this inequality right away thanks to this property from the sine function. And now, if you look at this series, what can we say? Does this converge or diverge? On the top we have 1, on the bottom we have n, and then plus 3 to the n. Which part is the dominating part? Comparison with 3 to the n on the bottom, right? Pick out the dominating part. So ignore the n, pick that up. So if you make a quick comparison, this right here is the series. N goes from 1 to infinity, 1 over 3 to the n. You see, Earlier we were adding things on the bottom, right? N is positive. Right now we took that away. So this thing will be less than, and I don't know why, but most of the time people write less than or equal to. I will keep that as well. Less than or equal to this. Yeah? So this right here, what kind of series is this though? It's a convergent geometry series, correct? This is geometric, right? And it actually converges because R is equal to 1/3. The absolute value of R is less than 1. And we can say that this right here also converges, right? Because we have this inequality already. So this right here converges. That means the original series converges absolutely. So of course, this one right here converges as well, right? So these right here are the first few steps and the idea. Most important thing is whenever you see sine n, sine of 2n, cosine of n, and so on, take the absolute value because we can use this right here right away. Right? I'll pause for like 10 seconds. Take a look. And if you guys want to see the whole worked out like written solutions, check out my 100 series video. Alright, so this one right here, it could be easy if you know the indications. And that's the goal for this video. When you see a series, it's not so bad sometimes. Alright, this is question number 24 for the next one. Here we're looking at the series, n goes from 1 to infinity, cosine squared of 1 over n. But for this one, do not do the absolute convergence. Will this stream be uploaded later? Yes. So after this is done, I will publish it. It will take some time for YouTube to process it. I'm pretty sure you can see it within like an hour. This is not alternating. You don't need a ratio test. Doesn't this diverge? Why? No, you don't need a double angle identity. Diverges, but why? Again, it's not a 50-50 guess, right? We have to write down the reason. Why does this diverge? Yes, first, test for divergence because of the limit test. So here we go. Test for divergence. Here we are going to check. Go ahead and check this on your own. Actually, I can finish this with you guys. We check the limit as n goes to infinity of the an. This right here is the an. So we check this. Cosine squared of 1 over n. Have a look. If you put infinity to here, we get 1 over infinity. 1 over infinity is 0. So we're looking at cosine square of 0. Okay, what's cosine of 0? When I do this, I'm telling you the answer already. What's cosine of 0? It's just 1, right? So this limit equals 1, and how can we utilize this 1? What do you have to say about this 1? It's 1, good, but so what? 1 is not equal to 0, thank you. Yes, it's not because 1 is greater than 0, well, technically yes, but all we have to mention is this right here is not equal to 0, so we can say this right here diverges by TFD. Okay? Alright, here's a question for you guys to try. Leave the answer down below, right? Especially for the people who come to watch the live stream later. What if I change the cosine to sine though? I'm going to leave this to you guys, right? Because this time, if you put n to be infinity, take the limit, this right here becomes 0. So test for divergence doesn't help. So go ahead and try this. Right, go ahead and try this. I'm not going to erase this yet. I will just leave it here so you guys can discuss in the chat. And we will go to the next question. This is question number 27 from the 100 series. N goes from 2 to infinity. Sorry, 1 to infinity. 1 over, ready? We have 2 to the ln n power. Right? And this right here, I'll leave that to you guys later. Now, let's focus on number 27. What do you mean P series? I don't see any power for P. Be careful, this is not geometric. Geometric is only when we have 1 over 2 raised to just n, but this is ln n. So what do you guys mean by P series? Now, how do we know it's a P series? Ah, yes, there's a nice logarithm property, right? So, ladies and gentlemen, have a look. Here, let me write that down right here for you guys. Today, if we have some number a raised to log base b of c, in fact, this right here is the same as c for the base, and then you change that right here, log base b of a. So this series here, it's the same as saying the series as n goes from 1 to infinity, and then we have 1 over the input, put that to be the base, and then the base, put that to be the logarithm here. So we have ln2, like that. This and that are the same, thanks to this property. So now what? This right here, now what? What's the conclusion for this? Is n to some power? ln2 is less than 1, yes. So, ladies and gentlemen, here, p is natural log of 2, which is about 0.693. More importantly though, you mentioned that is less than 1. Technically less than or equal to 1. So what's the conclusion? Converge or diverge for this? Diverges, thank you. So, just like that. Again, if you want to see the proof for this, I believe I proved that in the 100 series video, so you guys can go check that out. All right, next one we have question number 37 from the 100 series video. We have 1 minus 1 over n raised to the n squared power. So for this right here, I will also say there's a pretty clear indication of what test you should use. Root test, how come? How come? As I said, there's a clear indication. In fact, the nth term test for this doesn't help, because if you take the limit for that, you actually get 0. Because it's 1 minus 1 over n. If it's to the nth power, the limit for that is 1 over e, but this is n squared, you actually get 0. Ah, yes, you use the root test. Try the root test. I can only tell you to try because sometimes it might not work, right? Try the root test because we have n in the power. So it's a great idea. And let me write this down right here for you guys. For the root test, this right here is our an. And we are going to check the limit as n goes to infinity. And we take the nth root. And technically, we also apply the absolute value. And then you just put an in here. And I'm going to leave that to you guys to work that out. But for review purpose, when you do all the work, and then you get a number L, hopefully. And it's the same conclusion like what we had done before earlier with the ratio test. The series will converge if you see that L is less than 1, the series diverges if you see L is greater than 1. Again, sad face if L is equal to 1. Try another test. Test for divergence wouldn't work for this because, let me just mention this right away. If you have the limit as n goes to infinity of this 1 minus 1 over n squared, you actually end up with 0. The limit for this right here is 0 because it's n squared. But if you do the root test here, yes, the L here is 1 over e. All right. Okay, so I'll give you guys some time to kind of discuss this a little bit. And the phone is right in front of me, so I can see your chat. So if you leave anything in the chat, I can actually read it right away. And then we have 3 more to go. So regardless if you are taking a Cal2 class right now and use these videos to review, or if you just want to learn this for the enjoyment, yeah, that'd be nice. Done? Done? Okay. I hope to stream more this week because I know the final exams are coming, right? Especially, I'm also doing this for my students as well because their final exam is coming. All right, number 55. This is a little bit more difficult in my opinion. So series n goes from 2 to infinity, 1 over square root of n times ln n. Does this converge? I don't know if you guys can see all the tests on the back. You guys can take a look. Can go through all the choices and then just see which one will be for that. If you use the limit comparison test, you have to be super careful. If you use the limit comparison test, you have to, with 1 over square root of n, they cancel, and take the limit for this, you end up with 0. So limit comparison test is inconclusive. Ratio test is not a good idea because if you want to do square root of n plus 1 and then ln of n plus 1 and then divided by the original, in fact the limit I believe it should be 1, so it's inconclusive. Direct comparison with p-series, if you say so, you will have to come up with a p-series that you can compare with. And how do we know such thing too? No partial fractions because this is not even a polynomial, right? Partial fractions are for n to some whole number power. Yeah, rational expression. Direct comparison with, okay, if you guys said direct comparison test, you have to be careful though. This right here, we have 1 over square root of n, ln n, yeah? And if we compare this with 1 over square root of n, what inequality goes here? Let's just focus on this question. What inequality goes here? What inequality goes here? N begin with 2 to infinity. You can kind of just ignore that actually. Yeah, technically it's going to be less than if you just compare the expression, yeah? The starting number doesn't really matter that much. If you just have n goes to infinity, this is the inequality, but here's the deal. This right here, it's a divergent p-series because p is equal to 1/2. In fact, this right here gives us infinity. Okay, this is a true statement. Now, we know that this series is less than infinity. What can we say about this? Can we say anything in this regard? Nothing, because this right here, yes, it could be finite. It could be like 7, it can be 17, but it could be just a little bit smaller infinity. So we cannot say anything, unfortunately. So we cannot use the direct comparison test in this sense, right? So among all the tests, I think the direct comparison is the hardest one. Oh, hey, compare with 1 over n, but how do we know we use 1 over n? What's the hint? Nintendo Switch hint, thank you so much for the super chat. Thank you. No ratio test, no ratio test. Can we use the integral test? No, because remember, in order for us to use the integral test, you should ask the question, can we integrate this function? That before we talk about continuous positive decreasing, no. Can we integrate this function? No. Because ln is, so I have to go back to the chart. Is, okay, big O of square root of n. True that, and here's the thing. In Cal 2, we don't really do little o or big O notations unless like you are different schools. And usually this is what we can say. Here's a note, yeah, here's a note. This is a fact or note, whatever. The fact is, if you have ln n, this right here is always less than square root of n, and this is true for all n. And this is true for all n. So now if you just take the reciprocal on both sides, this right here means we get 1 over ln n will be greater than 1 over square root of n. Yeah, especially everybody is positive, so you can just reciprocate both sides without worry about the sign. Yeah. Now I'm going to multiply both sides by square root of n, so we get 1 over square root of n here, ln n. That will still be greater than 1 over this square root of n times that square root of n, which will give us 1 over n, isn't it? So as you can see, we have this expression being bigger than 1 over n. So this series right here, I'll just say this right here is bigger than the series as n goes from 2 to infinity of 1 over n. And we know this right here diverges. This right here is infinity. That this series is infinity. It's the divergent harmonic series without the first term, but still diverges to infinity. Therefore, what can we say about this? This right here also diverges by direct comparison test because we use the inequality. So direct comparison test is the way to go, but we have to make sure we do it carefully, and the inequality has to make sense. Yes, and I believe the direct comparison test is the hardest one among all the tests. So again, let me just show you guys. We have 10 series convergence tests right here. So also diverges, and of course you can write it down and all that stuff, or just check out my written solutions on my 100 series video. So that's that. Okay, two more questions. You still have to show that they are all positive. They are all positive because ln n is positive as n goes from 2 to infinity. This is like ln2 is 0.69. That's everybody is positive. So yeah. Okay. Number 56. Here we have the series as n goes from 1 to infinity. This right here, I would say it's one of them that has a clear indication as well. N minus 1 over n to the third power plus 2n and plus 5. You definitely have to know something like this for your Calc2 final. And for this kind of question, it's like straightforward. You can just do this and then most of the time will work. So let me know how do we do this. Nope, not the ratio test. Try the ratio test only when you have factorial or n in the power. Not test for divergence though, because you will still end up with 0. Direct comparison test. I wouldn't say direct comparison test because you have to do the inequality. It's not so easy to do the direct comparison test. Limit comparison test with 1 over n to the 3 over 2 power. That is correct. Just pick this up, the dominating part on the top, and then the dominating part on the bottom. And because the expression is slightly crazier, so try the limit comparison test. Will be easier. And you just do the limit comparison test with the series as n goes from 1 to infinity, n over, this is square root of n to the third power. So in another word, we are looking at n to the first over n to the 3 over 2. So if you do this, in fact, you can simplify it a little bit. Actually, I should have said compare with. If you subtract the exponent, this right here, you should have compared it with n goes from 1 to infinity, 1 over n to the 1/2 power. Reduce that. I don't know if you will work if you have 1 over n to the 3 over 2 power, but I think this right here works wonders. This right here, yes, because the p is 1/2, which is less than 1. Therefore, this right here diverges, and then do the limit. Take the limit as n goes to infinity. Put this on the top, over that on the bottom, and you'll see the limit is 1. If that limit is 1, is greater than 0, less than infinity, you get to draw conclusion for the limit comparison test. When you have 1 in the limit comparison test, the 1 helps because it's greater than 0. The 1 doesn't help if you have ratio test or the root test. Alright, so try that out. Alright, one more question, and that will be it for today. Take a guess what's the next one. Take a guess what the next one is. I have it here, so take a guess what kind of series it's going to be. There's one series that we haven't seen today, so which one is it? Not derivatives. The first one is alternating series already. The first question was alternating, so no. E to the n, that's kind of like geometric. What kind of series? Telescoping, yes, you can take a look right here. You are correct. And then some people said, yeah, e to the something. Yes, that's also correct. So number 70, we're looking at the series as n goes from 1 to infinity of e to the 1 over n minus e to the 1 over n plus 2. Yeah, for this. Yeah, telescoping is super satisfying. And now let me just remind you guys, this is a telescoping because this term and that term, they are pretty much the same kind, but they're just off by 2, right? The structure, it's the same. But here we have n, here we have n plus 2. So they're off by 2 terms. So this right here is telescoping. Telescoping. And remember, for telescoping, this is what you have to do. I'll work this one out for you guys. The fast way to do it is that, notice they are off by 2 terms. The bigger one is right here, right? The n plus 2 here. I mean the bigger one here. What we do is, Start with 1. Put it here 1 time. So e to the 1 over 1. And you add, the next number is 2. You put this down right here again. So it's e to the 1 over 2. Done with this. 2 terms in the front, and then we need 2 terms at the end. This right here, we need to subtract e to the 1 over n plus 2. And we also need to subtract one more term, minus e to the 1 over n plus 1. 2 terms in the front, 2 terms at the end. This right here gives you the Sn, namely the nth partial sum. This is the nth partial sum for this infinite series. And then we can just compute the limit as n goes to infinity of this. And perhaps let me just indicate that this right here is Sn, namely the nth partial sum. Then that's a fast way to do it. All right, let's finish this one together. What's the final answer? You need to have 2 terms at the end. So the last term is e to the 1 over n plus 2, right? So the previous term, so you just minus 1 to the index here. So you have the n plus 1. Unless you want to write out the whole thing and you see the cancellations, you will see that 2 terms in the front will be surviving and 2 terms at the end will be surviving. And that's how you get the nth partial sum for that. Be careful though, this is addition. We cannot combine any of them. How do we know this is a telescoping? Because firstly, a subtraction is a big hint. Secondly, e to the 1 over n, e to the 1 over n plus 2. You can see that the structures are the same, but they are off by 2. Here, you can look at this as a series as bn and then minus bn plus 2. In this case, bn is e to the 1 over n. And you see bn and bn plus 2, they are the same series, but they are just off by 2 terms. Okay, e to the first, I think you guys got it. E to the first is just e. E to the 1/2 is just square root of e. Are we done though? No, minus 2, correct. Because as n goes to infinity, this term goes to 0. As n goes to infinity, likewise, this goes to 0. E to the 0 is 1. E to the 0 is 1. So, final answer. We get e plus square root of e and then minus 2. And of course, this right here converges because we end up with a finite value. All right, cool. Thank you guys so much for coming today. Hopefully this video helps. And this video will be uploaded to YouTube later on. And if you want to see more serious practice questions, of course, check out my 100 series video. And then if you haven't done so already, download the worksheet in the description. All right? All right, until then, next time, limits and derivative. All right, bye.